Okay, let's dive into this. Welcome to today's explainer. Look, if you're tuning in, you already know wind energy is an absolute cornerstone of the global renewable transition. But today, we're looking way past the obvious. We're not just staring at massive towers and spinning blades. We are going to explore the highly technical, frankly fascinating world of wind turbine design innovations. Specifically, we'll be looking through the lens of the Sustainability Accounting Standards Board, or SASB, framework for wind technology and project developers, to see exactly how the industry measures a turbine's interaction with the real world. Get ready, because the engineering happening inside these machines is absolutely incredible.
So, let's start with a really tough question. What happens when green energy actually threatens local wildlife? It sounds like a total paradox, right? I mean, we build wind farms to help the environment. But the reality on the ground, or, up in the air, isn't always that ecologically simple. Building massive infrastructure in natural habitats introduces very real risks to birds, bats, and local ecosystems. And if project developers just ignore this, the consequences aren't just environmental. They hit the financials hard.
Which brings us to Section 1, the hidden challenges.
To understand how engineers are tackling these problems, we first need to look at the unexpected hurdles developers face way before a single blade ever starts turning. Now, in the wind industry, a developer's lifeline is their turbine order backlog, basically those confirmed future orders sitting on the books. But under the SASB standard known as RRWT 410A.2, developers and investors carefully track something called backlog cancellations. And these aren't just orders lost to a competitor. No, these are projects entirely shut down or delayed due to community or ecological impacts. We are literally talking about millions of dollars at risk here, all because a local community pushes back on noise or visual aesthetics, or environmental regulators step in over habitat risks. Bottom line, if a turbine doesn't fit harmoniously into its environment, the whole project just dies on the vine.
And this brilliantly illustrates exactly how the industry standardizes these risks. You can see right there under ecological impacts of project development, the metrics are laid out clear as day. ESG investors used this exact framework to measure the financial risks tied to those ecological challenges. They aren't just checking how much power a turbine generates anymore. They are looking at sound power levels, those backlog cancellations we just talked about, and, most importantly for us today, the specific design efforts made to mitigate these exact community and ecological impacts.
Moving on to Section 2, designing for the ecosystem.
So how exactly do you prevent your multi-million-dollar wind project from getting canceled by local opposition? Well, you design for the ecosystem. This brings us right to metric R-WT-410A.3. This requires companies to describe their efforts to address these impacts directly through the turbine's design. The days of treating a wind turbine like some passive, dumb tower just catching the breeze, those are long gone. Today's turbines are incredibly responsive, dynamic machines designed to actively protect their surroundings, whether they're sited onshore near local neighborhoods or offshore in super-sensitive marine environments. The industry tackles this through a really clever two-pronged approach. On one side, you've got physical technologies, actual hardware modifications built right into or added onto the turbine structure itself. Think specialized blade heating elements or advanced radar. Then, on the other side, you've got operational software. This is the digital brain of the turbine, usually managed through SCADA systems. That's supervisory control and data acquisition. These two sides work together seamlessly to mitigate risks to wildlife and local communities.
Let's break that down, starting with Section 3, Innovative Physical Technologies.
Let's look a little closer at that hardware. What kind of physical modifications are we actually talking about when we say a turbine is designed to protect wildlife? Honestly, some of this sounds like pure science fiction, but it is standard mitigation tech today. Take bird and bat deaths, for example. Developers are integrating wildlife detection radar directly onto the sites to spot incoming flocks. For bats specifically, they use ultrasonic deterrent transmitters. These are devices that emit high-frequency sounds that bats actively avoid, keeping them safely away from the dangerous swept area of the rotor. And then there are blade heating elements. Now, while these are primarily used to maintain efficiency and prevent dangerous ice throw, which, by the way, addresses a massive community safety and noise concern, this kind of physical tech ensures the turbine operates safely within its local climate without endangering whatever or whoever happens to be on the ground below.
Next up is Section 4, Smart Software and Curtailment.
But hardware is really only as good as the software controlling it, right? Let's move to the brains of the operation and see how this builds into a real-time defense mechanism for the ecosystem. Picture this scenario. Step 1, that wildlife radar spots a flock of endangered birds heading straight toward the wind farm. Step 2, the operational control software, the SCADA system, instantly receives this data and assesses the risk.
Step 3, it takes action through what the standard calls sudden curtailment capabilities. Basically, the software literally commands the turbines to brake and halt their spinning blades instantly. The flock passes by safely, and then the software just spins the turbines back up. I mean, these are practically living, breathing machines responding to their environment in real time. Another totally fascinating software trick is cut-in speed management. So the cut-in speed is just the minimum wind speed required for the turbine blades to start generating usable power. By integrating wildlife risk mitigation into this specific threshold, operators might program the software to keep the blades completely locked during lower wind speeds, say when certain at-risk bat species are most active. Sure, you sacrifice a tiny bit of low-wind energy generation, but you completely eliminate the ecological risk during those crucial hours. It's a brilliant, highly effective compromise managed entirely by software.
All right, Section 5, Material Efficiency in Design.
So we've seen how design protects the animals and the local community. Now let's shift gears slightly. Protecting the ecosystem also means being incredibly efficient with the massive amounts of raw resources required to build these gigantic structures in the first place. Under the SASB Materials Efficiency Metric RRWT 440B.1, developers have to track the top 5 materials consumed by weight. We're talking about staggering amounts of aluminum, carbon fiber, copper, fiberglass, and iron or steel. As turbines grow larger to capture more wind and generate more power, the sheer volume of material required just skyrockets. Tracking this isn't only about cost, it's about the environmental footprint of the entire supply chain. Optimizing these materials keeps production costs down, limits exposure to crazy raw material price swings, and shrinks the overall carbon footprint of manufacturing the turbine itself.
To truly measure this efficiency, engineers use a very specific metric called top head mass. As defined by the standard, this is the combined mass of the turbine nacelle, that big housing at the very top of the tower containing the generator and gearbox, and the turbine rotor hub, but excluding the blades themselves. It's measured in metric tons. But why does this specific measurement matter so much to developers and investors?
So the crucial point is this: it's all about the ratio of mass to power. The optimization strategy, outlined in metric RR-WT-440B.3, is to constantly innovate the design to reduce turbine and tower weights while simultaneously increasing the turbine's capacity, the actual megawatts of power it produces. Think about it. If you can generate 5 megawatts of power using a top head mass of 100 tons, and your competitor needs 150 tons of steel and copper to generate that exact same 5 megawatts, your design is vastly superior. You've maximized your capacity factor relative to the materials consumed. And that translates to higher margins, way easier transportation, and a much lighter footprint on the Earth.
Which brings us to our final section, Section 6, Measuring the Qualitative Metrics.
Let's bring it all together. How do the investors and project developers track the ultimate success of all these physical innovations, software curtailments, and material optimizations? Well, it all feeds directly back into the core activity metrics of the business. They track the number of delivered wind turbines and the aggregate capacity of the turbine backlog. Here's the bottom line. Successful design innovations drive these numbers up. If your turbines are lightweight, highly efficient, and packed with radar and software that actively prevent ecological damage, local communities and environmental regulators are going to approve those sites. Your backlog stays secure, your megawatt capacity grows, and deliveries actually happen. But if your design is ecologically disruptive, that backlog gets canceled. The qualitative design metrics directly dictate the quantitative financial success.
Which leaves us with a pretty massive question to think about. Wind turbines are only getting taller, and their swept rotor areas are only getting wider to capture more energy. As they grow larger and more dominant on our landscapes and coastlines, will our software, radar, and material design innovations continue to outpace our ecological footprint? The engineering we've looked at today strongly suggests they can, but it is going to require absolutely relentless innovation. Thanks for joining me for this explainer, and keep questioning how the technology around us is being built. Catch you next time.